reality is weird.
Far out in the remote ocean, wind speeds are higher, more consistent, and completely relentless. To capture that energy, engineers build massive modern wind turbines directly into the hostile marine environment. When you multiply that single turbine by hundreds, stretching all the way to the horizon, you generate gigawatts of raw electrical power. But generating that power is only half the equation. The traditional electrical grids on land were built around centralized power plants. They lack the physical storage capacity and the structural redundancy to absorb massive, sudden spikes of offshore wind energy. This diagram shows when a surge of wind power overloads the city grid. Operators protect the infrastructure by rejecting the excess energy. The turbines are physically cut off in a process called curtailment. The blades keep spinning, but the electricity is thrown away. The scale of this wasted power is massive. In the first half of 2025 alone, the amount of clean, renewable energy lost to curtailment could have powered every single home in Scotland. Building bigger offshore wind farms is futile if the electricity they produce remains stranded out at sea. The true bottleneck of the green transition is how we transport and store that energy. The only viable way to move up to 2.2 gigawatts of power across hundreds or even thousands of kilometers of ocean is a high-voltage direct current, or HVDC, subsea cable. The workers standing on these coiled lines highlight their massive physical scale. These are heavy, multi-layered structures engineered to endure decades of extreme environmental stress on the seafloor. Inside, a central copper or aluminum conductor carries the current. Surrounding it is a thick layer of cross-linked polyethylene, or XLPE. This specialized plastic insulation prevents the incredibly high voltage from breaking out of the cable and discharging into the sea. Outside of that insulation, the cable has to survive the deep ocean. A dense lead alloy sheath acts as a total moisture barrier, while heavy outer steel armor layers block thousands of pounds of incoming water pressure. Threaded right into this heavy armor are delicate optical fibers. They act as a continuous nervous system, pulsing with data to monitor mechanical strain and temperature changes along every inch of the route. Because most HVDC systems operate without redundant backups, this single, highly engineered wire carries an enormous burden. If it fails, the offshore platforms and wind farms connected to it instantly go dark. Laying thousands of tons of continuous cable requires specialized, dynamically positioned marine vessels. They use active thrusters to hold their exact coordinates in rough seas while feeding the cable down to the ocean floor. In shallow waters under 500 meters, the ocean itself isn't the biggest threat. Dropped ship anchors and heavy commercial fishing gear routinely snag and tear these cables apart. To protect them, remote machines use a technique called jetting. They fire high-pressure water swords into the seabed, turning hard sand into fluid, allowing the heavy cable to safely sink up to 3 meters below the ocean floor. In deep water environments past 500 meters, burial is virtually impossible. Instead, the cables are laid directly on the seabed, carefully guided into precise position by remotely operated vehicles. Even carefully laid cables face microscopic threats. If a tiny amount of moisture penetrates the outer layers, the intense electric field can cause branching cracks in the plastic insulation, a degradation known as water treeing. Eventually, this shorts out the transmission link. A single fault at the bottom of the ocean requires specialized deep-sea cutting devices and heavy lifting ships to pull the broken ends to the surface for repair. Until that weeks-long operation is finished, the entire offshore energy economy is paralyzed. Once the energy makes landfall, it moves from the subsea terminal directly into massive coastal industrial hubs. Here, offshore electricity powers massive industrial electrolyzers. Through power-to-gas, these facilities use the incoming current to split water molecules, generating pure green hydrogen. This animated flowchart shows exactly how this chemical conversion solves the curtailment crisis. It transforms those fleeting, unpredictable pulses of raw electricity into a physical gas that can be stored in tanks. These power-to-gas hubs act as high-capacity energy reservoirs. Converting the electricity into hydrogen decouples clean energy generation from the immediate second-by-second demands of the traditional electrical grid. Once you have physical hydrogen, the macroeconomic options open up. You can inject it directly into existing natural gas pipelines, or use it to decarbonize heavy, energy-intense industries like steel manufacturing and ammonia production. The success of this transition requires the offshore wind turbines, the subsea transmission lines, and the coastal electrolyzers to function together as a single, continuously integrated supply chain. But all these visible surface triumphs rely entirely on what happens thousands of feet below, where silent, armored subsea cables rest on the sand. The green energy transition requires massive infrastructure and complex chemistry, but none of it functions without these invisible lines of extreme engineering, quietly carrying the future of global energy to shore.